Okay, now this video is the second part of our video of the integral test, all right? And now let's continue with our second example here. If we have sigma n equals 0 to infinity of n plus 1 over n cubed, the first thing that we can realize is whenever we substitute n equals 0, there's a 0 in our denominator. We cannot divide by 0. We are not allowed to divide by 0. So what happens? Well, we can get rid of that 0. How? Well, we can change our interval, because this interval is actually from 0 to positive infinity, right? So what we can do is we can skip 0 and we can start from 1, right? We can make this interval, because if we plug in 1, then there's not a problem anymore. And the reason why we can do that so easily is because from 0 to infinity, there are a lot of numbers. And skipping just one number out is really not too much of an issue. All right, so we can do that very, very easily. So we can change the interval from 1 to infinity. Now, let's see if our four conditions are met. Number one, is this, well, let's actually rewrite this because we just changed it. This is now n equals 1 to infinity of n plus 1 over n to the third, okay? Now, is this function positive on this interval? And yes, so we can say, we can come over here and we can say a sub n is greater than 0 on, and we do have to specify what the interval is because we have changed the interval. Okay, so we can write it like this. So condition number 1 is met. Now, we can set this, for condition number 2, we can set this equal to the function x plus 1 over x to the third. Okay, now, so that's fine. Now, condition number 3, is this function decreasing? Well, we can compare the general terms. We can substitute numbers in here and see if the next numbers are decreasing. So let's do that. Let's substitute the 1 in there. So we have 1 plus 1 over 1 to the third power first. Okay, now this turns into 1 plus 1 is 2. 1 to the third is simply 1, because 1 to any power is simply 1. Now, so we get 2 as our first term. As our second term, okay, so this is our n equals 1 term. So our n plus 1 term, which means that our next term is equal to 2. And that would give us, let's just put those colons there. That will give us, substituting the 2 into here, 2 plus 1 over 2 to the third power. This simplifies down to 3 over 2 to the third power, or 2 cubed, is simply 8. Now, 3/8 is a smaller number than 2. So from this, we can determine that the more numbers that we plug in, our next terms, or our n plus 1 terms, will always be smaller, okay? So to say that it's decreasing, we compared the terms, we can say that a sub n is larger than a sub n plus 1. Again, n plus 1 specifying the next term. Okay, now we can also do this in the general sense, where we can compare this n plus 1 over n cubed. We can compare that to wherever we see an n, we substitute an n plus 1. Think of it as a composite function, okay, over n plus 1 to the third power. It simplifies down to n plus 1 over n to the third, n plus 2 over n plus 1 to the third. All right? Now, before, in our previous example of the harmonic series, our numerators were both the same. The only difference was that in our denominator. So we were able to very easily analyze these two fractions and determine which one was larger and which one was smaller. In this case, our numerators are also a little bit different. So it is a bit riskier to just look at the general term, okay? So instead of looking at the general term in this case, we simply plug in the numbers out. Or what we can do to find out if it's decreasing is we can say, or we can find the derivative, okay? So let's find the derivative of our function. Okay, x plus 1 over x cubed. Now f prime of x. All right, now let's look at this. This is actually one function divided by another function, and we're taking the derivative of that. What we can call that, the process is called the quotient rule. In this case, the quotient rule says x cubed times the derivative of the top. What is the derivative of x plus 1? Well, 1 goes to 0. The derivative of x is just 1. Okay, plus the top function times the derivative of the bottom, which is 3x squared, divided by the bottom function squared. Oh, I'm sorry, this sign in the middle should be a minus sign. Let's see if I did that correctly. Okay, yes, that is correct. And the general formula for this, let me just write the formula just in case you don't remember, and it might have been a while. For the derivative of f over g prime, okay, is equal to g f prime f g prime over g squared. All right, so that's just the quotient rule right there. And if you compare this to that, you'll see what I did. Now let's simplify this a little bit. We have x cubed minus, let's distribute over here, minus 3x to the third plus 3x squared divided by x to the sixth. This can simplify down into x cubed minus, this negative sign from here. It should be in parentheses, right? Because all I did was distribute that. So then this simplifies down into x cubed. Let's distribute the negative inside. Minus 3x cubed minus 3x squared divided by x to the sixth. We can combine like terms. X cubed minus 3x squared would simply give us negative 2x, x cubed minus 3x cubed will simply give us negative 2x cubed minus 3x squared divided by x to the sixth. Now, for any number on the interval 1 to infinity, if we plug it into the derivative, you will always get out a negative result. Let's just verify that. Let's just put in negative 1. So this comes into negative 2 times 1 to the third. I'm sorry, did I say put in a negative 1? I meant put in a positive 1. Negative 2 minus 3, 1 squared over 1 to the sixth. Simplifying this down, comes out to be 1 cubed is simply 1, so that's negative 2 minus 3, because 1 squared is 1, over 1. Negative 2 minus 3 is simply negative 5. Therefore, we get a negative result. If our first derivative is negative, what does that say about the original function? That says that the original function is decreasing. So, again, we are decreasing, and we have to put the interval here. We are decreasing on 1 to infinity. Are we continuous? And yes, we are continuous on the interval, and that's we had an asymptote at the 0 point, remember? And that's why we had to change our interval. So yes, we are continuous from 1 to infinity. There is no asymptote, hole, jump, etc. So if all 4 of these conditions are met, the integral test says to integrate the function. You can integrate the function by saying x plus 1 over x to the third, evaluated from 1 to infinity. And remember, we integrate based upon the new interval. And this is an improper integral, so we can write it as a limit. Limit as b approaches infinity of integral 1 to b, and I just changed that right there, x plus 1 over x cubed dx. Now, this one we have to do a little bit of work to integrate this. This comes down to being limit b approaches infinity. Now, I will go about this step by step. Of integral 1 to b of, let's split this fraction up. So we get x over x cubed plus 1 over x cubed. Well, this would be x. All right, let's simplify here, and let's bring this up. So this is equal to limit b approaches infinity of 1 to b x over x cubed. Okay, let me just write that. Let's see, where do I want to write that? Let me just write that right here. X over x cubed simplifies down into 1 over x squared. All right? If you have any question about that, this is simply rules of exponents. And with rules of exponents, also what I can do is I can bring this up as a -2. If you have any question about rules of exponents, send us a message and we'll make a video about that. So this is equal to x to the -2, and I can also bring this up, plus x to the -3 dx. All right, so far we haven't integrated yet, only simplified. Now let's try to integrate this. This becomes limit b approaches infinity of, all right, well, x to the -2, we can use the power rule, the general power rule for integration. Add the 1 on top, -2 plus 1 gives us -1, and divide by the result. So divide by -1, so x to the -1 divided by this -1 plus, and if you have any question about this is simply basic integration at this point. This becomes x to the -2 divided by -2. Okay, evaluated from 1 to b. Okay, let's simplify a little bit further. This is then equal to, actually I just still continue on this side, this is equal to limit b approaches infinity of, this we can simplify down into -1 over x. We can say that this is equal to -1 over 2x squared, and all this is evaluated from 1 to b. All right. Now this looks a little bit nicer than what we originally had. Let's use the fundamental theorem of calculus and plug and substitute our limits of integration in. Therefore, getting limit as b approaches infinity of, let's see, let's substitute the negative b in, or the b in first. So -1 over b, put in parentheses. So it's usually good practice to put everything that we substitute in parentheses. -1 over 2 times b squared minus -1 over x, or -1 over, in this case, we're substituting the 1, minus 1 over 2 times 1 squared. Okay, now we substitute that in. Now let's simplify this side of the limit first. Well, and let's simplify this side of the limit as well as substitute the b, the infinity in for b. Thereby getting -1 over infinity minus 1 over 2 times infinity squared minus, okay, -1 minus a half. -1 minus a half, that gives us -3 halves, minus -3 halves. All right. Now let's think about this part of the limit. -1 divided by a really large number. All right. Now what can we do about that? Well, let's think about this. If 1 is divided by 10, that's equal to 0.1, right? 1 is divided by 100, it's equal to 0.01. In other words, the idea is that as 1 gets divided by larger and larger numbers, this essentially the decimal starts to decrease. So in other words, the numbers start to decrease. So if 1 is divided by a really large number, then we can simply say that it simplifies down into 0, because these, as you can see, start getting really small. So we can say this simplifies down into 0. All right. Now let's think about this. And 0 is neutral, so we don't have to keep in mind. We don't have to keep the negative in mind. Infinity squared. Okay. Now a really big number is squared. That still results in a really big number. A really big number is squared and multiplied by 2 is still a really big number in the denominator. So a really big number in the denominator, infinity in the denominator gives us 0. So 0 minus 0 is still 0. Okay, now minus a -3 halves, so that's +3 halves because we changed the signs. 2 negatives make a positive. So this equals out to the +3 halves as the answer to the integral. Now, because we have a finite answer for our integral, we can look at this condition. Okay, we can say that this integral converges, and Now what this says is if the integral converges, then our series also converges. So because this interval converges, we can determine that this series is a convergent series because it fulfilled all 4 of these conditions. Okay. Now the last point I'd like to make is if any of these 4 conditions cannot be fulfilled, even by slightly altering the interval like we did over here, then we cannot use the integral test. We have to use some of the other tests, and we do have more tests that will be coming up in the future videos. Right? Thank you for watching, and if you have any questions, please let us know in a message.